Okay. So lesson 8, our lesson 8 corresponds with chapter 12 from the textbook, which is all about electron configuration. But before we do that, I want to review some stoichiometry with you. So here's a stoichiometry problem. How many grams of hydrochloric acid are required to fully neutralize 6.55 grams of sodium hydroxide? All right. So you'll remember from stoichiometry problems that we did prior to our break that in order to solve these problems, we need a balanced chemical equation, right? Right now, we do not have that. However, this is a chemical equation we have seen before. In fact, this is the one that we worked on our previous lab with. And so it's hydrochloric acid plus sodium hydroxide produces what?
Water.
Yep, this is an acid-base reaction. Absolutely, it produces water and a salt. And the particular salt that it produces are from the metal and the nonmetal attached in the acid, or the base and the acid, respectively. All right, so now we have our chemical equation. Now we need to balance our chemical equation. Okay? How many hydrogen are there on the left side of our equation? 2. How many on the right?
2.
Also 2. How many oxygen on the left? 1. How many on the right? 1. Sodium. 1 and 1. Chlorine. 1 and 1. So it's balanced. And not only is it balanced, but all of the coefficients are 1. Which is really, really wonderful when we're doing molar ratios to figure out how to convert from moles of one reactant to moles of a different reactant, or from moles of a reactant to moles of product. This is just wonderful. When this happens, you smile, you appreciate it, you love it. All right? Okay, so now when we look at this problem, the next thing we need to do is to determine the number of steps required to solve this problem. And as we look at this, do we have any ideas on the number of steps required to solve this problem?
3.
It's going to be 3. Because the first step, you'll remember that in order to convert from one material to another in our chemical equation, we have to know moles. So our first step is going to have to be to convert from grams to moles, because it gives us grams, but we can't do anything with grams other than to convert to moles of the same material. But it says how many grams of hydrochloric acid are required to neutralize 6.55 grams of sodium hydroxide. Charles? You're very welcome. All right. Then our second step is now we'll be able to go from moles of one material to moles of another. Right? We can do that only with molar ratios, only with moles. And then now we would be able to go back to grams in our third step. And so the more you do these problems, the more you'll learn to recognize that if it wants me to go from grams of one material to grams of another, it is going to require 3 steps. Okay? If it wants me to go from grams of one material to moles of another, or moles of a material to grams of another, I can do that in 2 steps. If it wants me to go from moles of one material to moles of another, I can do that in 1 step. Okay? Draw our horizontal line. Top left is what we're starting with, which better be 6.55 grams of sodium hydroxide, because if it isn't, we would have no idea of what to start with, right? That's the only measurement that our problem gives us. It's the only measurement that our problem gives us. And then top right, we want to put what we're transferring into. Okay, and what are we going into in this first step?
Moles.
We're going from grams to moles, and we can't go from grams of sodium hydroxide to anything other than moles of sodium hydroxide. It's the only thing we can do with grams. We'll carry the material down and to the right, but not the amount. In this step, we're going to go from moles of sodium hydroxide to what? We have two options here. We could go back to grams of sodium hydroxide. That doesn't seem helpful, right? Or we could go to moles of something else. Okay? We are going to go to moles of something else. And what is that something else? Hydrochloric acid. And we know we need to go to moles of hydrochloric acid because the problem wants us to determine how much hydrochloric acid do we need to neutralize the sodium hydroxide. Right? That's what the problem's asking for. Do you have a question, Josh? Okay. We'll carry the material down and to the right, but not the amount, which is good because we don't know the amount just yet. And then our last step, we're going to go to what? Grams. We better, because that's what the problem wants, and this is our last step. So we better get there. Grams of hydrochloric acid. Then you ask yourself, can we go from moles of hydrochloric acid to grams? You bet. So we'll carry this material down and to the right, but not the amount. And again, that is good because we do not yet know the amount. All right, now we have to start figuring out all of these coefficients. How do we know that we can put a 1 in front of both of those?
Because they're balanced equation.
Yeah, we look to our balanced chemical equation and there's a coefficient of 1 in front of both of them, which is what we use when we do the molar ratios. Now for these, I mean, you could choose however many moles you want, but choosing 1 is the simplest way to do it, right? Then you just go to your periodic table and you say, okay, well 1 mole of sodium hydroxide is going to have 1 mole of sodium plus 1 mole of oxygen plus 1 mole of hydrogen. Right? Would you agree with that? That 1 mole of sodium hydroxide is going to have 1 mole of sodium, 1 mole of oxygen, 1 mole of hydrogen. Okay? And then so we look to sodium and we find that it's what, 22.98. We'll just call that 23 grams. Okay, oxygen, we've talked about this before. We'll call this 16 grams. It's like 15.998. And then hydrogen, 1.0079. Is that what yours says?
6.7.
6.7.
Right. No.
1.0079.
Yeah,
79. We'll call that 1. Okay? So 23 and 16 is 39. 39 and 1 is 40. Okay? So 1 mole of sodium hydroxide is 40 grams of sodium hydroxide. Are you getting comfortable doing that yet? Done it a few times in this class. I don't know if you've ever done it before this class, but if that's the only thing you take away from that class, successful. That won't be the only thing, but if that were, at least you have something, right? It's like when you go on a trip and on the way back, you're like, oh, I didn't get any souvenirs. And then you just get like a little, trinket from the airport. I need something other than the pictures. Do you guys get souvenirs from your trips? Or do you not care? Oh. I like souvenirs. Anyways, 1 mole of hydrochloric acid has 1 mole of hydrogen plus 1 mole of chlorine. Hydrogen, we just talked about this, we'll call it 1 gram. Chlorine is 35.45, right? Is that right?
Yeah.
We'll call those 35.5 grams. Okay? We add those together and we get 36.5 grams. So 1 mole of hydrochloric acid is approximately 36.5 grams. All right, we're done, right? No, we're not. We got to make this a fraction and we multiply across. Wonderful thing about algebra is it tells us if we have something in the numerator and in the denominator, even if they aren't the same fraction, but the fractions are being multiplied, we can reduce them down. So this reduces with this reduces with this reduces with this. Look at that. That's why we draw it down and to the right, so that we can make that happen. And we'd be left with just grams of hydrochloric acid, which is wonderful because what is the problem asking us for? Grams of hydrochloric acid. And so we'll have 6.55 times 36.5 grams of hydrochloric acid divided by 40. It should be somewhere around 6. Has anybody done it? Because 36.5 is almost 40. So this would be just a little bit less than 1. A little bit less than 1 times 6.55. It should be somewhere right around 6.
5.976.
5.976. Wow. Let's just call that 6. 5.97. Let's just call that 6 grams of hydrochloric acid. What do you think? Do you like it? Do you love it? Do you want some more of it? Don't you worry, next week we'll do quiz number 3, and it will be entirely stoichiometry problems. You will get some more of it. All right? Now, are there any questions on this problem right now? Okay. We're going to introduce a new topic. It is electron configurations, and we're going to introduce it with this question. What is a metal? So I want you to take 2 minutes or so talking with those around you, and I want you to come up with a definition of what is a metal. What is a metal? All right, we have a definition of a metal. Josh. Okay. Tom, and then Charles. Are you passing, Tom?
Yeah, I'm not sure.
Charles.
Metals are good conductors for heat and
Electricity. Yep. And so a metal is an element that is a good conductor of heat and a good conductor of electric currents. Is that what you were going with? Yeah?
I just looked in the back of the book in the index.
It's not a bad idea. Not a bad idea at all. So let's talk, we'll actually define a metal 3 different ways. So one way we'll define it is that a metal is an element that freely gives up electrons to form to form positively charged ions. And we call these type of ions cat ions.
That makes no sense.
It doesn't make any sense because there's nothing positive about cats.
Cat ions? Zero sense.
Yeah, I convinced my class that there is no such thing as a domesticated cat. There are fat, lazy cats, but they are not domesticated. They are not domesticated.
That is true. My family has 30.
3 or 30? 3. I thought you said 30, and I was like, that is impressive.
We used to have 2 litters of cats, but we had to give some of them away.
Yeah, and the nice thing about kittens is everybody wants a kitten. No one wants a cat. So like, it's pretty easy to get rid of kittens. It is not easy to get rid of cats. Like kitten, oh, that's so cute. And then you have it for a while and you're like, wow, I hate this thing. And then you start letting it outside and hope the coyotes come and eat it. Right?
We do not want the coyotes to eat ours.
I understand. Some people like cats. I get it. Okay, so this is one way we'll define a metal. The next way is what the textbook says, is that metals are good conductors of electricity. Metals are elements that tend to be good conductors of electricity. Metals tend to be good conductors of electricity. Notice here it's a rule, but the tend to tells you that there are probably some exceptions to this, right? There are some things that are metals because they freely give up electrons, but they aren't good conductors of electricity for some reason or another. Last way we'll define a metal is this way. Metals tend to have the highest energy electrons in an s or a d orbital. And at this point, you should have no idea what that means. And then I know we're all on the same page, because I have no idea what that means. I'm just kidding.
If you do not know what it means, you would not be a good teacher.
I would not be equipped to teach you something I don't know. That is true. Although it's fun to try.
Quite nearly impossible.
Like I'm supposed to teach my children how to be good people. And I'm like, man, I'm not a good person. Do you ever feel like the Apostle Paul, and you read Romans 7, and you see the Apostle Paul's struggle, where it's like, the very things I want to do, I don't do, and the very things I don't want to do, those are the things that I do. And you read that, and you're like, oh my gosh, that's totally what's happening in my head. Sorry. Anyways, so what is a metal the last way? Metals tend to have the highest energy electrons in an s or a d orbital. Talk a little bit more about what that means in a few slides. But as you sum this question up, you might feel inclined to say see list, but we're not going to do that. We're going to take what is, I think, the best definition, and we will answer it that way. So what is a metal? Just say an element that forms cations. What is a metal? It is an element that forms cations. Now, the unfortunate thing is there are always exceptions to the rules, and you will find, I can think of at least one exception to that of something that forms cations and is not a metal, but it's unusual. That one will take you very far, very far. You're like, how far can a definition of a metal really take me? It's an excellent question. I don't know. And then I'd like for you to define cation. Cation. And so I told this to the class on Monday, that some people remember the differences in the terms of ions because they like cats, and they're like, cats are positive, therefore cations are positive. I don't like that one. So I came up with one on Monday. It just came to me. And the way you want to read this word is cation, right? We say it's cation, but it looks like it should be cation, which makes me think of a vacation, and that is a positive event. Yeah, you're welcome for that one. All right, our next question. What is a non-metal? What is a non-metal?
Water.
Water is a non-metal, but the challenging thing about that, Charles, is that water is a molecule, and so we tend to define these as individual elements. Like, is an individual element a metal or non-metal? But you are right, that water is certainly a non-metal, and it is made of two non-metals. And so this is one where we'll actually answer it before I give you any of the information on the slide. Best way to answer this question, what is a non-metal, is this way. It is an element that is not a metal. It is an element that is not a metal. That's what a non-metal is. It's an element that is not a metal. And that may be dissatisfying to you, and if it is, I'm sorry. It's the best way to define a non-metal. You're like, why can't we have something like? I mean, we'll add some pieces. So we'll define a non-metal three ways. First way, a non-metal is an element that typically takes on electrons to form negatively charged ions. Man, I changed all of these, and they're back. Hang on. I changed these grammatical errors on Monday, but they apparently didn't save. So nonmetal is an element that typically takes on electrons to form negatively charged ions, and we call these anions. Anions. And I know what you're thinking, Dr. Engel, this is really frustrating, because if O-N-I-O-N is onion, why is A-N-I-O-N not anion? I don't have a good answer to that question. Or why isn't onion pronounced onion? The answer is, start a movement, right? To change the way we pronounce onion to onion.
Change Arkansas to Arkansas.
Arkansas. Okay. Nonmetals tend to be poor conductors of electricity. Notice when we said a nonmetal is an element that typically takes on electrons. This one, there are a lot of exceptions to that rule. There are a lot of exceptions to that rule. So that's why for this one, I think the best way to define a nonmetal is to just say it's an element that is not a metal. But nonmetals tend to be poor conductors of electricity. And then the last way, nonmetals tend to have the highest energy electrons in a p orbital. Tend to have the highest energy electrons in a p orbital. And again, at this point, you should have no idea what that means. You should have no idea what that means. But we'll talk about that in just a moment. So we've already answered this question, right? What is a nonmetal? It is an element that is not a metal. Profound, I know. That is a profound definition. It's like, what is a cat? It is an animal that is not a dog, right? Or you could, anyways, sorry. There's a saying that any dog less than 40 pounds is a cat, and cats are useless. I read that up on the board. Anyways, in the Bible building. Okay, so we've already answered this. I'd like you to look up anion. Anion. Also known as anion. That's not true. All right, next question. What are orbitals? Because we've talked now about S and D orbitals, and we've talked about P orbitals, but we haven't even talked about what an orbital is. What is an orbital, or what are orbitals? So remember from a previous lecture that electrons are located around the nucleus, right? They surround the nucleus. What's inside the nucleus?
Electrons?
No, electrons surround it. Protons and neutrons. Do you remember talking about this a few weeks ago? Okay, so electrons surround the nucleus. Now, as they do, they reside in orbitals. They reside in orbitals. And you're like, well, that's wonderful. You still haven't told us what an orbital is. What are orbitals? Well, remember that electrons are around the nucleus. They reside in orbitals. Now, let's determine what an orbital is. Orbitals are three-dimensional spaces that include up to 2 electrons. So orbitals are three-dimensional spaces and you'll see this as you continue your progression through chemistry, that different orbitals have different shapes, but they're all three-dimensional spaces. Yeah, Josh?
Is dimensional spelled?
Dimensional? I think so.
That's kind of weird in the middle. I don't know, that's just me.
I'm pretty sure, but I don't know.
It's like dimensional.
I think it's S is
Like,
down.
maybe.
Right?
That's right.
It didn't tell me it was wrong. But, I mean, spelling and I don't get along very well.
Same.
So three-dimensional spaces that include up to 2 electrons. That is incredibly important to remember, the up to 2 electrons. There are 4 different types of orbitals. There are s orbitals, there are p orbitals, there are d orbitals, and there are f orbitals. And they're all a different shape. Unfortunately, they are not shaped like the letter, because that would be really nice. So there are 4 different types of orbitals: s orbitals, p orbitals, d orbitals, and f orbitals. Each orbital type makes up what we call a subshell. So we would say something like the p subshell, the s subshell, the d subshell, and what else? And we already used p. We haven't used F yet. The F subshell. So each orbital type makes up what we call a subshell. Yeah, Ethan.
Why is it a question mark after the third point? Sorry, I just...
No, it's fine. That was another thing that I erased on Monday, and then it stuck around. Okay, now I'm going to make sure it saves. I don't know. I told this to the group on Monday. I wrote these slides at a time when my brain was not working very well. All right, so S subshells have 1 orbital. S subshells have 1 orbital. Meaning that an S subshell can contain how many electrons? 2. Each orbital can contain up to 2 electrons. So if an F subshell has 1 orbital, it can contain up to 2 electrons. All right? P subshells contain 3 orbitals. P subshells contain 3 orbitals. 3 orbitals can hold how many electrons? 6. D subshells contain 5 orbitals. Which means how many electrons? 10. And F subshells contain 7 orbitals. Okay? How many electrons can you have in an F subshell? 14. 7 times 2. Nice. So last point from this slide is as the energy level increases, so as we go from the first energy level to the second energy level to the third, fourth, fifth, sixth, seventh, the size of the orbitals increase and the variety of orbitals increases. So as energy level increases, the variety of orbitals increases, and the size of orbitals increases. How many orbital types do you think you find in the first energy level? Just 1. What about in the second energy level? 2. In the third energy level? 3. In the fourth energy level and following, we have all 4 of our orbital types. So the fourth energy level, 5th, 6th, and 7th, we have all 4 of our orbital types. All right? That make sense? So on Monday, we answered this question this way. What are orbitals? We said they are tracks for electrons. Tracks like T-R-A-C-K-S. They are tracks for electrons. And that's the best I can think of. And I hope when you read that, you don't think a two-dimensional track, because this is a three-dimensional track. This is like a submarine race. Okay? Where it could go left, right, and it can increase in depth and decrease in depth. Okay? It's a three-dimensional track. Do they really have submarine races? I don't know.
Or an airplane race.
Or an airplane race, yeah. Or
Airplanes cannot go up there.
a hot air balloon race.
Hot air balloons can only go up. Or wherever the wind takes them.
Wherever the wind takes them, like a jelly, right? Jelly can only swim up and down, but it goes where the water takes it.
Interesting race.
The sea jelly. That would be an interesting race. I mean, you could put like a little motor on it and get you some propulsion. All right, so are we okay with this one? Any questions? Okay, so I want to show you this. This is your periodic table, but instead of showing all of the elements, what it does is it shows you the highest energy electron for each element. Okay? So let's say we were talking about hydrogen. Hydrogen is right here. Do you agree? Looking at your periodic table, this is hydrogen. And so rather than writing hydrogen, it's telling us that its highest energy electron is in a 1s orbital. Okay? First energy level, we already said that there's only one type of orbital there, and it's s. And its highest energy electron is in a 1s orbital. Happens to only have one electron, by the way. I don't know if you remember this from several weeks ago, but the atomic number, which is written in the top right on your periodic table, that tells you the number of protons and the number of electrons for a neutral version of that element. So when you look at hydrogen, what number is in the top right? 1, which means it has 1 proton and 1 electron in a neutral form of that element. Okay? Make sense? Cool. Now let's talk about arsenic. Okay? Arsenic is right here. AS. Do you see it there? AS. You see it wrote out arsenic. Okay? What is the number in the top right of arsenic? 33, which means it has 33 protons and 33 neutrons in a neutral form of this element. Okay? And then this tells us that the highest energy electron for arsenic is in what orbital? 4p. Okay? Its highest energy electron is in a 4p subshell. And according to our definition of nonmetals, nonmetals tend to have their highest energy electrons in a p orbital, right? So arsenic, by our definition, at least by that definition, it would lead you to believe that arsenic is a nonmetal. Okay? Is that all right? Okay. Any questions about this? We're going to come back to this, but we need to introduce now electron configuration, which is what this whole lesson is titled. We'll go to the title slide, not the actual title slide, but where we actually use that term. We'll talk about electron configuration, then we'll come back to this chart. Okay? We okay? All right. So what is an electron configuration? This is the last question we'll deal with. Sort of. Because then we'll have questions of like, what is the electron configuration for? All right. So what is an electron configuration? It is a representation of every electron in the atom. We just talked about where the highest energy electron is, right? On the previous diagram, we talked about where the highest energy electron is. The electron configuration, though, represents every single electron in the atom. As you read from left to right across the periodic table, or left to right across your electron configuration, the energy level increases. I forgive you.
Barely.
I was going to say I'm also sorry, but I'm not. Okay, so as you read left to right, the energy level increases. You must fill, those of you that have the class on Monday, you didn't see this because I added it. You must fill the lower energy levels before you can go to a higher level.
Just like you should always start from the beginning of a book to the end of it.
Absolutely. I agree. Although sometimes I'm too anxious. I have to know how it ends. Do you ever watch movies with somebody who's seen the movie before and you ask them how it ends just to deal with your anxiety? Nah, it's me. I'm like, I'm too anxious to wait. I need to know. And then I'll still enjoy the movie and see how we get there. Sometimes I need to know the ending.
And people who tell you the ending, you don't ask.
Oh, I know. That happens all too often. I did that in one of my classes the other day, but it was a movie that's like 15 years old. Like, if you haven't seen that movie yet, you're probably not ever going to see it. So then I used it as an illustration. All right, you must fill the lower energy levels before you can go to a higher energy level, okay? We just talked about arsenic, right? Using that chart, and we said arsenic has 33 electrons, right? And we said that the highest energy electron is in a 4p orbital. If we're going to get that highest energy electron into a 4p, we have to fill every orbital that came before 4p. Okay? We've got to fill 1s. We've got to fill 2s. We've got to fill 2p, and 3s, and 3p, and 4s, and 3d, and 4p. We got to fill them all before we can get to those highest energy. Which makes sense, because we got to find a place for 33 electrons to reside. If each orbital can only hold 2 electrons, we need 17 orbitals to contain 33, right? And we got to fill them up lowest energy first. All right. Keep in mind that every atom wants a completely filled p subshell as the highest energy. That's what every atom wants. That's when atoms are most stable. That's something to keep in mind as you work through your homework for this chapter. It's something to keep in mind for the rest of this school year. That this drives a lot of the reason why elements behave the way that they do. And it's because atoms want a completely filled p subshell as the highest energy. Completely filled. All right? You want to put this into practice? Because you're like, Dr. Engel, oh, at first we need to answer this question. What is an electron configuration? Right? See first point. SEE, FIRST, POINT. See first point. It's a representation of every electron in the atom. All right, the rest of the information on this slide is to help you to know where do all the electrons go. Where do they go? Where do they go? All right. So, what is the electron configuration for oxygen? What is the electron configuration? I'm actually going to I'm going to put all of them on the board that are on this slide, and then I want to go back. Wow, that's not good. Too high. Too high. Okay. So we have oxygen, sodium, and potassium. So we want the electron configuration for oxygen. We want the electron configuration for sodium. We want the electron configuration for potassium. All right? And the beauty of this is the question, the framing question, didn't finish until after oxygen, after sodium, after potassium, meaning these are 3 different framing questions, and the answer is just going to be the electron configuration. It's beautiful. Symmetry. Okay? All right. Let's go back to our diagram. All right. So let's take a look at this. We're going to do the electron configuration first for oxygen. And so if we look at your periodic table and compare it to this, we find that oxygen is right here. Yes? Telling us that its highest energy electron is in the 2p subshell.
2p4.
Okay? It is 2p4. Does it give the electron configurations on your periodic table?
Yes, it's right under the...
For all of them?
Yep.
Oh, but it shortens them. It shortens them down. Anyways.
Yep.
So oxygen, we're going to get all the way to 2p, but we have to fill every orbital, every subshell that comes before 2p. So to get to 2p, we've got to read left to right, top to bottom, just like you would a book. So what comes first? 1s. And how many electrons can fit in 1s? 2, right? It's an S subtype. And S subshells only have 1 orbital. 1 orbital can hold 2 electrons.
It says that it has 1s, 2s, 2.
2s2, yep, because then the next one is 2s. That's the next subshell. And an S subshell contains 1 orbital. 1 orbital can hold 2 electrons. So now we have accounted for...
And then the 2p is 4.
It is, you're right. But we've accounted for 4 electrons. If we look in the top right, it tells us how many electrons oxygen has. What's that number in the top right? 8, right? So a neutral version of this element has 8 electrons. We've accounted for 4 of them, telling us that the remaining 4 are in this highest energy subshell. 2p4. Okay? Watch this. How many electrons can a p subshell hold? 6, right? 3 orbitals, 2 electrons each, 6. There's 1, 2, 3, 4, 5, 6 elements grouped in this p section. Coincidence? Let's check. How many electrons can an S subshell hold?
1.
1 orbital, 2 electrons. 1, 2. How many electrons can a D subshell hold? 10, right? 5 orbitals, 2 electrons each. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What about an F? 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. No longer looking coincidental. This is the reason why the periodic table is shaped the way that it is, and why it isn't just a block where you read all the way, why we don't just put this up and read, like a table, left to right, but why it's structured this way. That's cool stuff, right? And then we look, oxygen is right here in the 4th position. So we're like, can we do 2p1, 2p2, 2p3, 2p4? And you absolutely can. It's so wonderful. So there's multiple ways that you can remind yourself of how to come up with a proper electron configuration. You can do it based on the total number of electrons. You can do it based on where it's positioned in this figure. You can do it based on where it's positioned in this block. Okay? So let's do this again. But now for sodium.
3s1.
Yeah, but see there, it shortens it. It's only giving you, we'll talk about how you do that. So it put, what did it put? Neon in brackets. Does it have neon in brackets? Which is telling you that it has the full electron configuration of neon plus 3s1. Okay, but we've got sodium, it's right here. Yes? So its highest energy electron is in the 3s subshell. But in order to get to that, we need to fill all of the subshells that come before it, right? What's the first subshell we need to fill?
1s.
1s, and it holds how many electrons?
2.
2. Then we'll fill 2s. And how many electrons does it hold? 2. Then we'll fill what?
1,
2p, yeah. So remember, the second orbital type doesn't come till the second energy level. The third orbital type, being D, doesn't come until the third energy level. And the fourth orbital type, F, doesn't come until the fourth energy level. All right, so 2p, and how many electrons can the 2p subshell hold?
6.
6. And then finally, we'll get into 3s, and we'll figure out how many electrons have we accounted for? 2, 4, 10. How many electrons does sodium have according to the top right number? 11. So we've already accounted for 10 of them. How many of them are in this subshell?
1.
Just 1. Okay? So here's the electron configuration for sodium. The periodic table takes all of this and replaces it by neon, which has this electron configuration. Okay? So we could have done it that way, or we could also just look, here's where sodium is, and it's in the first position in 3s. So its highest energy is going to be 3s1. Or again, you can do it by the total number of electrons. Now let's do this for potassium. Where is potassium? It's right here, right? So its highest energy electron should be what? 4s1. And now let's see if it makes sense based on total electron type. Okay? If we're going to fill all the way to 4s1, we've got to fill everything that came before it. What's the first orbital we're going to fill?
1s.
1s. And how many electrons can that hold?
2.
2. Then we're going to fill what?
2.
2s. And how many electrons can that hold? 2. Then we're going to fill
2p.
2p. And how many electrons can that hold? 6. And then we're going to fill
3s.
3s comes next. And how many electrons can that hold? 2, because it's an S subshell. And then we're going to fill 3p. And how many electrons can a P subshell hold? 6. And now we've accounted for 2, 4, 10, 12, 18 electrons. How many electrons does potassium have according to the atomic number? 19. Which means that we need to put 1 into a 4s orbital, because that's the next orbital to come. Okay? So again, you can do it based on the total number of electrons, or you can do it just based on, okay, potassium is sitting here, this is 4s1. What about if it were sitting here? It would end in what? 3d1. You notice 3d is higher energy than 4s. That's frustrating, because you're like, this is the third energy level, this is the fourth. But it's because of the shape of those orbitals. So 3d is actually higher energy than 4s. But you would know that by looking at your periodic table. And then when you look at 4f, it actually fits in right here. No, it fits in right here. So 4f is higher in energy than 6s, than 5p, than 4d, than 5s. These f orbitals, because of their shape, are actually really high in energy. Very unusual. But if we were dealing with this element here, where would its highest energy electron be? In the 4f subshell, and it would end with 4f3. Okay? And then so if you want, you can shorten any of these electron configurations by putting the most recent noble gas that you pass by, the thing all the way at the end. Because remember, I told you in the previous slide, atoms want what? They want the filled p orbital to be their highest energy level. So that's this row here has satisfied that. Every element sitting here, they're already satisfied. They have exactly what they want. So if you were to make a prediction about how reactive these are, what would you predict? Are they very reactive or not very reactive? They are not varied. They already have exactly what they want. Oxygen, how many p electrons does it have? 4. How many does it want? 6. So what do you think oxygen is going to tend to do? Gain 2. And what are things that tend to take on electrons and form anions? What are those? Nonmetals. Oxygen is a nonmetal. Okay, sodium. It has 1 s electron. What do you think would be easier for it to do? To get rid of this and to go back to a fully filled P? Or to gain 7 electrons? 1 more in the S and then 6 more in the 3P.
Get rid of the S.
To get rid of the 1, right? So it's going to tend to get rid of electrons and become positively charged cation, which is the definition for what?
Metal.
A metal. So sodium is a metal, potassium is the same. Alright? Sound good?
So,
It is 1:45. It's actually 1:46 now. But did you have a question, Charles?